Automation has transformed industry, and one of the key innovations behind it is the Programmable Logic Controller or PLC. Since the 1960s, PLC have played a crucial role in streamlining industrial processes, offering flexibility and reliability in automation. Garage door, however, have not fully utilized automation potential. Many still rely on manual operation, lacking safety mechanisms that can prevent accidents or obstruction. Our project aims to bridge this gap by developing a PLC-based automated garage door system with integrated safety sensors. This system will provide convenience, efficiency, and enhanced security for users. Traditional garage door comes with several challenges. Many require manual operation, which can be inconvenient, especially during extreme weather or emergencies. More importantly, this system lacks built-in safety mechanism. Without obstacle detection, there is a risk of property damage or even injury if a person, pet, or object is in the way when the door closes. Additionally, most conventional systems do not utilize real-time decision making. They rely on basic mechanical components rather than smart automation. This means they cannot respond dynamically to different conditions. To address this issue, we propose an intelligent, automated garage door system that ensures safety, efficiency, and ease of use. Our project focuses on achieving two key objectives. First, we aim to design an automated garage door system that incorporates safety sensors like infrared and strain gauge sensors. This will detect obstacles and prevent accidents during operation. Second, we will implement PLC-based control logic to automate the door movement. The PLC will process real-time data from the sensors and ensure precise and safe operation. With this objective, we are developing a smarter, safer, and more reliable garage door systems that enhance user convenience.
The system will utilize infrared sensors for object detection and strain gauge sensors to detect resistance during door movement, preventing accidental collisions. The safety mechanism will be programmed to stop or reverse the door movement when obstructions are detected. Next, the control logic for the system will be developed using a PLC. The logic is designed to process real-time sensor input and control the motorized movement of the garage door accordingly. Moreover, ladder diagram will be created and simulated using PLC Fiddle, which is an online PLC simulation tool. So the project will focus on the control and automation aspects, including sensor integration, ladder logic programming, and also functioning testing through simulations. There were many existing garage door that has been equipped with automatic feature. First example is automated garage door using infrared sensor and Arduino. This system offers two methods of operation, which remote control access using a series of button press and automatic trigger using a vehicle-mounted IR transmitter. So second, get equipped with Bluetooth sensors and a mobile-based control interface. The system allows automatic activation when the user's phone comes within proximity, signaling the Bluetooth module to trigger door movement. Third, integration of IoT into garage systems. The system support voice commands through Google Assistant. And also not only that, they implement real-time notifications and user authentication, which ensures the only authorized individuals can control the system. PLC play a fundamental role in industrial automation by offering a reliable and efficient means of controlling equipment and processes. It was originally developed in the late 1960s as a replacement of hardwired relay systems, and today they are integral components of modern industrial and control systems. The International Electrotechnical Commission's EIC established IEC 611313, which standardized five primary PLC programming language, which are ladder diagram, function block diagram, structured text, instruction list, and sequential function chart. Among all, ladder diagram is the most widely used because it closely resembles electrical relay logic. Based on the figure on the right, we can see that the main components of PLC is consists of input section, output section, and CPU, which have their own functionality. Active infrared sensors emit their own IR signal and detect reflections, often used for proximity and obstacle detection, while passive IR sensors, or PIR, detect thermal radiations commonly applied in security and automation systems. It is popular due to their own low cost, compact size, and non-contact operation. Meanwhile, strain gauges measures the strain or deformation of a material when subjected to force. The working principle is based on the change in electrical resistance of the gauge as it is stretched or compressed. This change is proportional to the amount of strain, allowing for accurate stress analysis.
Next, we continue with the methodology for the system component. So we have three devices. That is the input devices, output devices, and the processing unit. So for the input devices, first we go to the open or close button. So its function is to initiate the door opening or closing sequence. Next, for the stop button, it acts as an emergency stop function. So if any emergency happens. And then the next one is the optical encoder. So this is one of the sensor being used. So it acts as a fully open or fully closed switch, which determine whether the garage door has been fully open or fully closed. And then we will use so for this optical encoder, we will use the incremental encoder. And then we also use the strain gauge sensor that will act as the overload sensor. It will detect the overstrain or obstruction during closing or opening of the door. And then the next one is the infrared sensor. It will act as a safety sensor. It will detect any obstruction that comes between the garage door and the floor during closing, then send signal to reopen it. We continue with the output devices. So the first one is the motor. So the motor will open or close the garage door, and the LED indicator will give the signal either the garage door is opening or closing. And then there's also the overload LED light that will give the signal of the garage door if it is overstrained or if there is any obstruction. And then the last one is the processing unit. So we'll be using the PLC because it is more suitable for this situation. The next part for the methodology is the logic formulation. So this one, it just tells about how the system works logically. So the first one is the when open button is pushed, so the light turns on, the open light will turn on, and then it will start the delay opening timer, and then the motor will run to open the garage door. And then when the door is fully open, so the optical encoder will detect the full open position, and then the motor will stop and the open light will turn off. Next, when the close button is pushed, the close light turns on, and then the delay closing timer will start, and then the motor will run to close the garage door. When the garage door is fully closed, the optical encoder will detect that it is in full closed position. The motor will stop and the close light will turn off. So by using the optical encoder, we will get a precise garage door precise position whether the garage door is fully closed or fully open. So we'll utilize the value like 0 equal to garage door at fully closed and 50 at the equal to garage door at fully open. Next, for the safety features, we have the infrared sensor. So when obstruction happen, the infrared sensor will detect obstruction under the garage door when closing, and then it will stop the motor and it will reopen the garage door. The next one is the strain gauge sensor. It will detect when overload happen. So the strain gauge sensor will detect strain due to obstruction or overstrain. So it will stop the motor. It will stop the motor, and the overload light will turn on. And then the user need to push open button to continue open or push close button to continue close. So it's a little bit different. The infrared sensor will return to open position, and then but the strain gauge sensor will just stop the garage door. So this is the system design, and besides it, we have the flowchart for opening the door. So the system will start when the open button is pushed. So when the open button is pushed, the open light will turn on, and then the delay opening timer will be activated according to what we said, like maybe 10 second or 5 second after we push the open button, and then the motor will start to run to open the garage door, and then the strain gauge will start to functioning. So it will detect if there is any change of resistance. So this one is it will detect if there is any overstrain, maybe like something stuck between the motor or something. If there is no change of resistance, so it will continue with the system. So it will continue with the stop, but it will check either the stop button is being pressed or not. If there is no stop button being pressed, it will continue with the optical encoder. So the optical encoder will detect either the value has reached 50 or not. So if it is still not reaching 50, it will continue. It will return to the above, return to the front. it will restart the loop and the motor will continue to run. And then and it will continue looping until the value reach 50. After the value is equal to 50, so the motor will stop and the garage it, and when the motor stop, it detects it is the garage door is fully open. So when the garage door is closing, it will start with the close button is being pushed. The close light will turns on and the delay closing timer will be activated. And then the motor will run to close the door, the garage door, and then the IR sensor will be start to functioning. It will detect either if there is any obstruction. So if there is obstruction, so the motor will run to reopen the garage door. But if there is no obstruction, it will continue the system. So the next one is the strain gauge. Strain gauge will detect either there is any change of resistance. It means that if there is anything stuck or overstrain or overload. If there is no, it will continue, and then it will check either the stop button is being pressed or not. If there is no stop button being pressed, it will continue with the optical encoder that will detect if is the value equal to zero or not. If it is still not equal to zero, it means that the garage door is still not fully closed yet. So it will continue the loop until the value for the optical encoder it detects up to zero. So if it is up to zero, then the motor will stop and it indicates that the garage door is fully closing.
Now let's move on to the result and discussion for our ladder diagram. This ladder diagram represents the core logic behind the control system of our project. It was developed using PLC programming to ensure both functionality and safety. There are two key highlights to emphasize here. The first one is logical control. This refers to how the system defines specific condition for motor operation, safety interlocks, and user input. For instance, the motor will only operate when the correct button is pressed and all safety sensors are in the appropriate state. This prevents the system from functioning under unsafe or undesired conditions. Second is real-time decision making. This means the PLC responds instantly to sensor inputs. For example, if an obstruction is detected or the overlap protection is triggered, the system is immediately halt the operation. Such quick responses are essential to avoid accidents and prevent system damage. Now, if we look at the ladder diagram on the right, we can observe how each rung represents specific condition for different actions. The first rung introduces a delay before opening the door. It checks if the stop button is not pressed, the door is not fully open, and there are no overloads. Once these conditions are met, it activates the open delay. This is followed by the third rung, which activates the motor to open the garage door. Similarly, the second and fourth rung handle the closing operation. The second rung applies a delay, while the fourth rung triggers the motor to close the door again, ensuring all safety conditions are satisfied. Additional rungs are programmed to the first one is to reopen the door if an obstacle is detected during the closing process. The second is to activate the safety light in the event of an overload. And finally, automatically close the door if it remains open beyond a specified duration. In summary, this ladder diagram enables our system to make intelligent real-time decisions based on sensor inputs and user commands, ensuring smooth, safe, and efficient operation.
Hello and welcome. So now we will demonstrate the PLC circuit for automatic garage door. So in this demonstration, we will showcase the working of an automatic garage door control system using a PLC circuit. We will go through 5 key scenarios to understand how the system operates and ensure safety. So for scenario 1, let's begin with the normal door opening sequence. So when I press the open button, the open light will turn on, and then there is a 3-second delay for the motor to operate, and then it will start moving the door upwards. So this timer is to ensure that the door operates with the precision and avoids abrupt movement. So as we can see, The open light is on, indicating the door is in motion. The motor remains active until the door reaches its fully open position. Now that it has reached its fully open position, the motor stops and the system ready for the next operation. Next, let's observe the normal door closing sequence. So when I press the close button, the close light will turn on, and after the 3-second delay, the door will start moving downward. So the close light is on, indicating that the door is closing. The system will continue moving until it reaches its fully closed position. So now that the door is fully closed, the motor stops, completing the cycle. Next, we will demonstrate the safety features of this PLC circuit. So in this scenario, we will test the overload protection feature. Suppose there is a mechanical jam or excessive load on the motor. So for example, like the open button, we turn on the open button. So we're ready on overload protection. So as soon as the system detects the overload, the motor stops immediately to prevent damage to the motor, and the overload light is turned on, signaling a fault. So in this state, the system does not respond to command until the overload condition is clear. Next, so now let's test the safety sensor features. So imagine there is an object in the path where the door is closing. So we turn on the close button. Wait until it turn on. Okay. So the moment the safety sensor detects an obstruction, the system stops the motor and automatically reverses the door back to the open position. So the door will remain open until the obstruction is removed, and the user manually restart the closing process. Alright. So last but not least, let's test the emergency stop feature. So if at any time an operator needs to stop the door immediately in case of emergency, they can press the stop button. So the stop button, boom, it will immediately stop the button. As you can see, the motor stops instantly and the door remains at its current position. So the system is now idle until further action is taken. So that concludes our demonstration of the automatic garage door control system using a PLC circuit.
Based on the demonstration presented by Faiz, there are 4 key points we can highlight in our discussion. First, the PLC ladder logic we implemented successfully controls the entire operation of the garage door. It accurately processes inputs from sensors and user buttons to execute smooth and reliable opening and closing actions. Second, we integrated infrared and strain gauge sensors to enhance operational safety. These sensors detect any obstruction or excessive force during movement, allowing the system to respond immediately and prevent potential accidents. Third, we tested the emergency stop function, which worked efficiently. When triggered either manually by the user or due to system fault, the motion stopped instantly, adding a vital safety layer to the system. Finally, we added LED indicators to provide real-time system feedback. These indicators display the current status of the garage door, whether it's opening, closing, idle, or in error, offer users a clear and immediate understanding of what the system is doing. In conclusion, the demonstration detected that our system performs reliably in terms of control, safety, and user feedback, meeting all intended functionality.
Through this project, we successfully integrated PLC-based automation with safety sensors to create an intelligent garage door system. By utilizing real-time sensors feedback, our system ensures smooth and efficient operation while prioritizing safety. The inclusion of infrared and strain gauge sensors allows the system to detect obstruction, preventing accidents and damage. This makes the garage door more reliable and user-friendly. Moving forward, this system has the potential for real-world implementation with further improvement in automation, connectivity, and energy efficiency. Thus, to enhance the system further, we propose 3 key improvements. First, smart control and monitoring. Integrating IoT technology will allow users to control and monitor the garage door remotely via a mobile app or voice assistants like Alexa or Google Assistants. Second, improve safety and efficiency. Adding more advanced sensors such as ultrasonic or camera-based detection can enhance obstacle detection. Additionally, using energy-efficient motors can reduce power consumption. Finally, feature expansion. Our system can be extended to support multiple garage doors and license plate recognition. With this enhancement, the system can become smarter, safer, and more efficient, ensuring long-term reliability and convenience for users. This concludes our video on the automated garage door control with safety sensors. Through this project, we have demonstrated how PLC-based automation and safety sensor can enhance efficiency, reliability, and security. This is all from our group. Thank you.